Okay, this is problem 6120 in Hibbeler. This is not really a unsymmetric bending problem, but it is a bending where we have bending in two planes. Since what we have here is a shaft that holds three pulleys and is supported at two bearing points, A and B. All right, the whole shaft is allowed to rotate. The reaction forces A and B hold in an equilibrium, at least every degree of freedom except for the rotation on the x-axis, obviously. And you want to find, well, the allowable stress in the shaft is 150 megapascals, and then your job is to design D, the diameter of the shaft. Since it's a circular shaft, the bending planes are going to be coincident with principal axes, obviously. Okay. So how do we go about doing this? Well, the first thing we're going to have to do is a basic statics problem. We're going to have to determine the reaction forces at A and B, because we really need those to be able to do the first step, which is then get the bending moment diagrams. And if you look at this problem, what you'll see is there's actually this 300 Newton force at both of these, or actually it's 600 total, causes bending in the y x plane. And then the forces at pulley C and E cause bending in the zx plane. All right, so we're going to have to consider those separately. So we're going to need to get the bending moment around the y-axis, that's the bending in the zx plane, and then also the z bending moments. All right. Once we know that, we'll have to then use that to figure out which points have the maximum stress, and then use that in design equation. Okay, where S is equal to I over C. That's the shape factor. So basically use this to solve for S, right? So from this we get S is going to equal the maximum bending moment divided by the allowable stress. This is the geometric shape factor. That's what's going to let us determine the diameter D. All right? We're going to get the maximum bending moment from this step, and then sigma allowable is given. All right? So that's the basic procedure. Well, before we, we can get this shape factor completely in terms of the outer diameter, right? The shape factor is I, which is pi over 64 d to the fourth, divided by c. C is just d over 2, and so that gives me pi on 32 d cubed, right? So that's the shape factor. So in fact, we can use that into here and solve for the diameter. Okay, so let's get the reaction forces first. Okay, so if we look at, let's just first look at the z forces. Let's draw that. I was going to skip drawing the free body diagram, but let's not do that. All right, so this is point C, A, D, B, and E. At C, and I'm going to say this is the, we're going to do this in the xz plane, right? So at C, we have a minus 400 newtons, and we have a minus 300 newtons at point E, right? That's the two 150 and the two 200s. D has nothing acting downward, and then we have the reaction forces at A and B. So we're going to call this force at A in the Z direction and force at B in the Z direction. Okay? So again, just doing this real quick. FAZ plus FBZ has to equal the 700 newtons. And then let's do sum of moments around point A. So this is sum of moments. These are sum of moments about the y-axis and about point A. And if you look at the way this is, y is going into the page, right? That's the y-axis going into the page. And so the positive moment around the y-axis is actually going to be clockwise, right? So that's a positive moment. And that's going to give me, each one of these is a half a meter, right? We got half meter, half meter, half meter. So the moment arm of this one around A, that's a negative 400 times 0.5. This one does nothing. This has nothing. Then we have this is another negative moment, FBZ. Its moment arm is 1. And then we have a positive moment of 300, and its moment arm is 1.5. That all goes to 0. So that gives me that FB in the Z direction is equal to 300 times 1.5 minus 400 times 0.5, which equals 200. It's a minus 200. That's 250 newtons. I'm sorry, newtons. Okay? And then we can do that. We can use that into here, and that tells me that FAZ is going to be the 700 minus 250. Okay? We'll do the same thing in the y plane, the yx plane, and get the forces in the y direction. Just move that up a little bit. So basically I have the same picture. Here are the bearings. Okay, now this is going to be the x-axis, and this is now going to be the y-axis. This is C, A, D, B, and then E. And the only force here is the minus 600 at point D. I mean, the only one that we know. And then we have the external reaction ones here. Force at B in the y direction, force at A in the y direction. All right, they obviously have to add up to give me 600. You can do the moments, but then just from looking at this, it's symmetric, so they have to be equal as well. That's a little out of focus, isn't it? There, that's a little better. So this is going to tell me that FAY has to equal FBY, and those have to equal 300 newtons, okay? So that's the 0th step I just did here, right? Step 0. Okay, next, now that we know the forces, we can get the bending moment diagrams. And we'll have to get a bending moment diagram in both these planes. One in the XY plane, and in the XY plane, the positive bending moment is counterclockwise. And also in the xz plane, right? This one gives us the y moments, and this one gives us the z moments. All right? Okay, so let's do that now. Well, this one's pretty simple. Let's first look at this. So, make sense. Is it positive? Are these going to be positive or negative ones? It's going to go. Yeah. So these are going to be positive. Here's the x direction, and this is going to be the z moment. Okay. Now, as we take sections from point C to point A, there's no forces. There's no moments, right? It's only at this point where we get to A. Let's label points on here. So this is C, A, D, B, and E. So we have 0 moment from C to A. Okay? Now once we go out to here, between A and D, this point force is going to give me a linear moment. You know, it's this force times this distance. So as I move out, the moment increases linear. It's going to be a positive moment because this one's going to induce a moment going this way. So the internal reaction moment that balances that is going to be a positive one. And the slope of that is going to be FAY, which we know is 300 newtons and 300 newtons. Why do I know that? Well, you can write I'll do it once and you can see why. At this point here, I have 300 newtons, or in general some force. Here's the internal reaction moment. This distance here is going to be x minus this distance, which is the 0.5. So the moment is actually equal to 300 times the moment arm. All right? So whenever you have a point force, it's going to put a linear moment in the moment diagram, and the slope is always going to be equal to the value of the point force. All right? This is just going to give me a little offset point. So this one starts to go up with a positive slope of 300 until we get to this point. So this is 300. So that means if we go a half of a meter, that this will go up to the value of 150 Newton meters, right? That will be the moment at that point. All right. Now, once we go past that point, right, between D and B, let's do the same sort of argument. I'll do it a little more quickly, I should say. Now we start to see the effect of the 600 Newton force. So this one still has this linearly increasing with a slope of 300. But now we get this moment here. This is going to add a moment. The moment from this force is going to be 600 times x minus this distance from here to here is 1. So it's x minus 1. And it's a negative moment. So I get a negative on there, right? Because that's going to tend to go this way. So the moment that's going to resist it is going to be a negative moment. So here you can see this is going to add on to this. And so the slope is going to be minus 300, not 300. And that'll bring me back down to 0. And then once you get past this point, well, again, you can see here the force is 0 if you do sections from the right-hand side, or this is all in equilibrium. So they all cancel out, and that's it. All right. So that's the moment diagram. This is for bending in the y-x plane. Or in other words, that's the bending moment about the z-axis. Okay? So the max is going to be at point D. That's the critical point. All right, let's look now at the other plane. Here's x. Now we're looking at the bending moment around y. We're at the same points. C, A, D, B, and E. Okay? But now the forces look a little different. So between C and A, the only thing we have between C and A is downward 200 newtons. This distance here is going to be x. Well, in this diagram, right, the positive moment actually is clockwise. So on this phase, a positive moment will actually be this way. That's the my moment. Positive from the same reasons we talked about before. Okay? So if you look at this one actually is going to be well, it's going to be the right sign, right? This is going to introduce negative moment balanced by the positive moment. So this one's actually going to equal 200 times x. All right, so this is going to start off here at 0 and have a slope of 200 until I reach this point. So that's 200, 200. So that means that this value here is going to be 200 over times its arm of 0.5. So that's going to be a value of 100 Newton meters. What am I doing? Newton meters. Okay. Except that this isn't, I'm sorry, this isn't 200, it's actually 400, right? Because it's two of them, sorry. So I actually should have 400 here, which will put a 400 here. My apologies, which make this have a slope of 400. And this is now 200 Newton meters is the max at that, right? So that's 200 Newton meters. Okay. Actually, let's make it a little easier to see. I think it'll be better. I think that'll be the max actually. So let's make that go up to about here. So this slope here is 400 Newton meters. And that means this point here is going to be 200 Newton meters. Okay? So that's up to this point. Now once we get to point A, we still have that moment, but now we're adding on to it. So I still have the 400 times x moment from this one, but now I have an upward force at A of 450 newtons. Right? So this one is going to give me a moment with a slope of positive 400. It's still a positive moment. So this one's going to give me a moment with a slope of minus 450. So this one's going to have a slope of minus 450. This one has a slope of 400. So the net slope is going to be minus 50. So from here down, it's going to drop minus 50. So that's so think about here. It'll drop like this. But this slope here is going to be minus 50. So that means from here to here, this is a distance of 0.5. and that's going to keep going, right? There's nothing at D, so actually we have the same state all the way between B and A. So this will carry all the way over to point B at that slope of 50, okay? And so that means the total drop here is going to be 50 times 1 meter, so that's going to be minus a 50. So that means this is going to drop down to the moment at this point, 150 Newton meters, all right? Then we know that the moment should also drop down to 0 here, but just to check, right, you're going to have another contribution at this point, at B, the point force, which is 250 newtons. Wait, did I get this right? Right, 250 newtons. The point force, so this has a slope of minus 50. Then we're going to have to drop the slope off of it of another 250, so that's a slope of 200. There's something still weird about this. No. 250. The slope was at minus 50. So when we drop off another 250 off the slope, it becomes minus 300 over half of me. It goes down to 0 here, right? So every time you add a point force, the slope of the curve will change by the value of that point force, right? That's what I was getting at here. The other way to do it is you can look right at point E. We look at it from the right-hand side. Here's point E. We have the downward 300 newtons here. And the moment, this is a negative phase, so the positive moment is going to be that way. So this moment is going to be minus 300 N, and this distance is going to be the total length minus X. So that's X minus 2 meters, right? That's that distance. Okay? And so it gives me this one here that has a slope of 300, again over the half that brings you down to the bottom. So this is the total moment diagram. I should probably say that again. So I've done plenty of these examples where I do the, actually explicitly draw the free body diagrams like that. And you can check that as well. But what I'm saying is when you're doing these and you have these point forces, it's kind of easy to directly or graphically construct the moment diagram, right? The change in the slope of the moment diagram is going to be equal to the point force. So when we go from C to A, there's no point force, so the slope is 0. Once we go to point A, we have a 300 point force. You have to check the sign, whether that's going to be a positive bending moment or a negative bending moment. In this case, it's a positive bending moment. It has a slope of 300. So it goes in that slope of 300 until we get the effect of the 600 point force, the 600 Newton point force. That's going to give me a minus 600 plus a 300. So the net slope is going to be minus 300 until you get down to B, at which point from B to E, the net force is going to be 300 plus 300 minus 600. So that's 0. All right. Likewise, when we go from here, from C to A, where's the actual diagram? From C to A, no, this is the one. From C to A, right? First we have the 400. This one turns out to give us a positive bending moment because the positive bending moment sense flips in that plane. So it slopes up at 400 until it gets to point A. And at point A, we have the difference of these two. So we have 400 down, and then 450 up positive 400 and a minus 450. So the net slope is minus 50. The next place you get a point force isn't until B. That the point force is 250. So minus 250, minus 50. So that comes down here at a minus 300. Okay? And the reason that works is because when you look at the moment arms, you're always going to have the force multiplied by the moment arm, which is x, minus something else. You'll never get an additional factor in here. So the slope is always going to be equal to the value of the point force. All right. So anyway, now we have the bending moment diagrams. All right. Where are the maximum stresses going to occur? Well, there's really 2 points. Okay. We have to be worried about point D and also point A. All right. So, although the absolute the maximum value we have here occurs at point A. At point A, you have the 200 Newton meter bending moment, which is the biggest thing on this whole diagram. D only has a value of 150. But if you look at the other mode, right, in the other plane where this is 200, this is 0. So it doesn't add anything onto here. Now, in contrast, if we look at point D, where the Z bending moment is maximal, or the bending in the YX plane is maximal, there will also be a contribution in the other plane, right? So we need this, actually we need that bending moment as well. So here we know it's 0, right? So here it's 0, here it's 150 Newton meters, here it's 200 Newton meters, and then here at D, it's going to be 200, 150. So this is going to be 175 Newton meters. So we really need to check both of these points, okay? The combined stresses from both of those points. All right. So let's draw the picture. Maybe it'll be a little clearer of the logic. I don't know if I'm explaining it too well right now. So let's look at, we're going to consider both points. Points A and D. And we're going to consider the contribution from both of the bending moments. So let's first look at A. So this is A. Okay, so here's the cross section. And here's the shaft going down. So this is the x-axis. This is the y-axis. And this is the z-axis, okay? All right. So at this point, we know that we have a bending moment about the z-axis is equal to 0 Newton meters, and the bending moment around the y-axis is 200 Newton meters. So actually at this point, we really just have one contribution of stress. It's really only due to this. So that's the bending around the y-axis. So that means I have a bending moment like this, right? This is we're bending around this with a 200 Newton meter force. So that means if I look at this cross section, right, we're going to get a compressional stress that breaks out, and then we're going to have an extensional stress at this point. So we're going to be compression on this end, and then tension on that end. Okay, so this is supposed to be coming out like, in that plane, right? So actually, it's just a regular bending problem. So the maximum stress is going to occur here and here, and it's going to have a value. This is at point A, just coming about from the bending in the y plane. All right. So it's going to have its max moment, 200 Newton meters. The greater outer fiber distance is from here to here, so that's going to be a plus or a minus the diameter on 2 over, oops, I'm sorry, this is a design problem, so I should, sorry. Okay, so here's where the maximum stresses are going to occur. All right, so now we can design the diameter, right? So we know that we already figured out that I on C is the pi on 32 diameter cubed. So we can set this around, we can get that S is equal to the maximum bending moments at point A over the allowable. Or that's just going to be 200 Newton meters over the allowable, which is the 150 pascals, right? 150 megapascals. 150 times 10 to the 6th newtons per meter squared. And that's going to give me an S equal to 1.33 times 10 to the minus 6th meters cubed, all right? So if we were just considering point A, to support the bending moments at point A, the diameter would have to be such that S equals this. Or in other words, pi on 32, the diameter cubed, has to equal 1.33 times 10 to the minus 6th meters cubed, where that'll give me a diameter equal to, let's multiply this by 32, divide by pi, and then take the cube root of this. And that gives me 0.024 meters. Or in other words, that's 24 millimeters. That should be the diameter, okay? That's just considering the stresses at point A. The worst case scenario might actually turn out to be at point D, so we have to consider that case as well. So let's look at point D. And point D is where it gets interesting because here we get both of the bending moments. So let's draw the same picture. So now we're going to consider point D. So I should have made this bigger. Here's the x-axis. Here's the y-axis. Here's the z-axis. This is point D. All right. Now, at point D, we have two bending moments. We have the M about the Z, which is equal to 150 Newton meters of bending. And then we have the Y, which is 175 Newton meters. Okay? Okay. So let me draw those stresses, okay? So let's first do the moment around the Z. So that's in red. So that's a moment like this of 150 Newton meters. I'm sorry, Newton meters. So that means this side's going to be in compression, this side's going to be in tension. All right. Vanishes, that should go right through the origin. So that's a stress distribution on that cross-section from bending around the z-axis. But also we're going to have a contribution from bending around the y-axis. So if we look at the y-axis, it's also positive. So that's going to be going this way of 175 Newton meters. And so this side's going to be in compression and this side's going to be in tension. So this one's going to come out in tension. This one's going to go in compression. So we can draw that. So somewhere on this face you're going to have a maximal, right? So this is kind of tricky. If you look at this point, right, at these 2 points, at 6 o'clock and at 12 o'clock, right, you're going to get no bending stress from the MZ. And likewise, if you have, just consider 3 o'clock and 9 o'clock, you're going to have stress only from the moment about the z-axis, and that's the neutral axis for the bending about the y-axis. So actually what's going to happen here is, well, this is the quadrant where they're both in compression. So actually somewhere in here there will be a maximal value in, this will be some max tension, and then somewhere in here, wait, did I get this back? Okay, sorry. I'm doing this wrong way. Let's be careful. This is tension from the blue stresses, and this is in tension from the red stresses. So somewhere along here is going to be the max tension. And then somewhere along this edge, the red's in compression, and then also the blue's in compression. So somewhere along here is going to be max compression. Now what you're actually going to find is these lines will, these points will be 180 degrees apart from each other, and then the perpendicular to that will actually be the neutral axis, right? Because the the max stresses are perpendicular to the neutral axis. Now here, it's a little tricky. You say, well, where does it happen? But this is, if you remember, when we looked at the neutral axis equation, right? Let's look at the cross sections. Let's look straight on. Here is y. Here is z. All right, so if we draw the moment as a vector, what happens is I have 175 in z. So let's say, let's kind of measure this out. So let's say we do 50. Let's do this as 50. 50, 100, 150, and this would be about 175. And then the component in the z direction is 150. So it's 50, 100, 150. They're both positive, so they're going in that direction. So this actually would be the moment vector. Okay? So this is the moment vector. All right? And it's going to have a value of square root of 150 squared plus 175 squared. Right? Because this is going to be 175 and this is 50. All right? So this has a value. The slope of this is going to be 175 and the slope of this is 150. Or in other words, this thing has a slope of, common denominator is 25. Right, so this is 4, that's 7, and this is, so another way of writing the slope is, this is 7, and then 25 goes into here, 4, 5, 6, so that's 6, all right? But this magnitude here, we can get as follows. That's 230 point, well, let's just leave it there. 230 Newton meters. Okay? So that's the 230 Newton meters. Well, now that you know the magnitude of the bending moment, all right? Basically, the bending plane now is perpendicular to this, right? This is the bending plane. All right? And now, since this is a circular cross-section, I should probably define all the angles. So the positive angle is going to be this way. No, it's this way, actually. We're doing it negative. So this angle here is the theta angle. And if you look at the equation, the angle for the neutral axis location, let's see if I get it the right way. I forget whether it's z or y. It actually doesn't matter. Okay? Let me look it up. I should just get it right. It's z on y. Yeah, okay. It's z on y. So I got it right. But these eyes are the same because it's circular cross-section. All right? So this is actually going to be 1. So that means the tangent of alpha is going to equal the tangent of theta. Or in other words, this plane here is going to be the neutral axis. All right? And so that means the maximum stresses are going to occur here. Or in other words, this would be just the same as if I considered a problem where I call this the y direction. Okay? If this were not a symmetric cross-section, if it were like an I-beam, that would be a little more complicated, all right? You have to go back and find out where the neutral axis is and then use that to determine where the maximal stresses would be, okay? Okay. So now actually I can treat this just as if it were a symmetric bending problem where the bending moment were 230, all right? So now I know that the shape factor has to be the maximum bending stress over the allowable stress. Now in this case, this is the max stress. So that's the 230 over the 150 megapascals. And that's going to give me 1.53 times 10 to the minus 6 meters cubed. All right? So now we use the same relationship. We know that S is, for a circular cross-section, is pi on 32 d cubed. And that'll then give me pi on 32 d cubed has to equal 1.53 times 10 to the minus 6th meters cubed. Solving for d, this gives me that d is equal to 25 millimeters. All right? And so at point D, you need to have a shaft of at least 25 millimeters. From the prior analysis, they're pretty close actually. The shaft was supposed to be 24 meters. You get a 24 millimeter shaft. So actually the correct answer is dictated by the case at point A. So this is actually going to be your answer. But more conservative, right? All right. All right. So just in summary, it's a little confusing. The first parts of the problem, you have to go through the basic analysis. Since it is a design problem, we have to get the bending moment diagrams, at least to that point. So we do that. That's pretty straightforward. But now at this point, we have bending in two planes. Okay? And so actually, we'll look at points where they're maximal in each plane. So here, for the z moment diagram, we should look at point D. And here for the y moment diagram, it says we should look at point A. So we want to consider both of those points. We have to consider the combined stress, the combined bending moment problem. At point A, it's simple because the z moment vanishes. Okay? So you know that the shape factor has to equal the maximum bending moment over the allowable stress. Now doing the same thing at point D. Now at point D we have both stresses, all right? So we can figure out the total bending moment, the net vector, right? The my and the mz are the components, so that gives us a total bending moment of 230 newton meters at this orientation where you're going 7 this way and 6 this way, right? That's the direction. Okay, so perpendicular to that is the bending plane. All right. Now, since this is a symmetric cross-section, IZ and IY are equal, the location of the neutral axis is going to be perpendicular to the bending plane. If it were an I-beam, that would not be this situation necessarily, okay? So then we can actually treat this just like a regular symmetric bending problem in the bending plane, all right? So the max bending moment at this point is the 230 newton meters. We divide by the allowable stress, that gives us the shape factor that we can solve for D. And obviously, you want to pick the biggest diameter, okay? Although 24 millimeters will work at point A, it doesn't work at point D, all right? So that's the answer.